All right, next lesson for probability. We are doing 12.2 experimental probability, and we're going to just do simple events. So I can find the experimental probability of simple events. So experimental probability is still a ratio of the number of times an event occurs to the total number of trials or times the activity is performed. So it's like if I flipped a coin 50 times, that's my total number of trials, and I got tails, 32 times. So my experimental probability would be 32 out of 50. A simple event is an event that only has one single outcome. So like flipping a coin, I can only get tails or heads. Only one thing can happen. Rolling a dice, I can only get one number. Pulling a card, we only pull one card at a time, so that's why it's a simple event. So one outcome for every time I do it. Pulling, remember last time I talked about pulling socks out of a drawer? I only pull out one pair of socks. So a single thing can happen. Okay, so this is just a reminder, an example of what is experimental probability, right? So it's a ratio, a fraction of the number of times the event occurs, the total of that event, and then out of how many times you did the experiment. Okay, so you can see the root word experimental comes from experiment. So actually doing it. So Martin has a bag of marbles. He removed one marble at random, recorded the color, and then placed it back in the bag. He repeated this process several times and recorded his results in the table. So this is his results of his experiment. Find the experimental probability of drawing each color. So there's 4 colors, so we're going to have experimental probability of each. This is a simple event because we're only pulling one marble at a time. Okay, so there can't be multiple things happening. So you'll notice we need the total, and there is no total. So we're going to add the total to our table here. That means we need to add these up, just like we did in our quizzes for making inferences, right? 10.2. So 5, 6, 7, 8, 9, 10, and then 1, 2, 3, 4, 5. So there's a total of 50 trials. We need that to start, okay? So let's do the probability of red. Remember, this is how we write it. So red had 12 out of 50. So there it is. And then we always reduce, just like we did in 12.1. So 12 out of 50. Sorry, divide by 2. And we will get 6 out of 25. So there's the experimental probability for red. So let's do probability of blue. Okay, so 10 out of 50. We always reduce. This one will reduce by 10, and we'll get 1/5. Okay, so let's have you pause and get the experimental probability for green. And do the experimental probability of yellow. I want to see if you can do them. This is where you should pause and try them on your own and check. So for green, we have 15 out of 50. We can reduce this by 5, and we get 3 out of 10. And then yellow is 13 out of 50. And guess what? We don't reduce because 13 and 50 don't have something in common. So there's all of my experimental probabilities for each. Red, blue, green, yellow. All right, a spinner has 3 unequal sections, red, yellow, and blue. The table shows the results of Nolan's spins. Find the experimental probability of landing on each color. And it even reminds you to put them in simplest form this time. Okay, so we need the total, so we're going to add that again to our table. 6 and 4 make 10, and then 1, 2, 3. So this is where I would like for you to, again, pause based off what we just did on the last one. Probability red, probability yellow, and I'm going to put this one over here just for space, probability of blue. It's really important that you pause and try to do this yourself. So we're going to go 10 out of 30, reduce simplest form, 1/3. 14 out of 30, reduce 7 out of 15. All right, divide by 2. And then blue, 6 out of 30, reduce 1/5. That one's divided by 6. All right, to play a game, you spin a spinner like the one shown. If you win, the arrow lands in one of the areas marked win. Lee plays this game many times and recorded her results. She won 8 times and lost 40 times. Find the experimental probability of not winning, so that'd be losing, right? All right, pause. You see if you can do the whole process this time, right? So I'm not going to do anything. We want to find the probability of not winning, which would also call the probability of losing. Losing, no E, I-N-G. All right. All right, so the first thing I have to do is find the total, right? 40 times lost, 8 times won, and so we would do that he played the game 48 times. He lost 40 times, and then we would need to reduce this. You could do it by 2, you could do it by 4, you actually could do it by 8 and get 5 out of 6. So that would be the experimental probability of Lee not winning, which is losing. All right, so things to remember: experimental probability of an event is the number of trials. Oh, nope, not number of trials, I apologize. Number of event over total trials. There we go. And then remember, always reduce, which means simplest form. All right, that was a fast one. So here's your independent practice. We've got Micah and Joan are on the same softball team. Micah got 8 hits out of 48 times at bat, while Joan got 12 hits out of 40 times at bat. Who do you think is more likely to hit her next time at bat? Ooh, a little extra step. You have to compare them. Okay, so you have to find their experimental probabilities and then compare them, right? So we have Micah. Let me do it this way. Probability, Micah. Probability, Joan, and then compare. Alrighty. Until next time.